Following our discussion about arcs at infinity, this is an example to demonstrate that, and this is an example that we started off this class with, where it has one pole at the origin, one open loop pole at the origin, and two open loop poles at -1. And so we saw this root locus diagram before, and we know that at k is equal to 2, this system becomes marginally stable, and then once k is bigger than that, then it becomes unstable. We've already kind of looked through all of these Bode plots, and so what's new is to take a look at the Nyquist diagram and also take a look at how it uses this arc at infinity. And in this case, it's a half loop. And the idea is that, remember, the Nyquist diagram shows all values along the entire imaginary axis. And so here there are angles that are associated with this minus end of the imaginary axis. So if we were to take a point here, this pole at 0 would point at an angle of -90. These two poles over here would both contribute a minus angle of this degree. And then once it jumped over to the positive x-axis, y or imaginary axis, now we're located here. And at that point in time, now this pole at 0 is now contributing a +90, and these two poles over here are contributing this positive value. So in between, the contribution from these two poles will dwindle down to 0 and then build up from 0. But it's this pole at the origin, and specifically it's the one that's on the imaginary axis, that's essentially going to flip from -90 to +90. And because of that, we see this jump, this arc at infinity in the Nyquist diagram. And one of the things I'll mention here is just kind of from a practical side, I like to use the Nyquist diagrams that Mathematica uses. So you can use Wolfram Alpha or use Mathematica, the program, to plot these. It does a slightly better job of showing you these arcs at infinity than MATLAB does. So one of the consequences of the arcs at infinity is the fact that this Bode diagram, effectively, we'll put this in air quotes, quote unquote, starts at -90, because at this point that's very, very close to essentially this point right here, that's very, very close to the origin, but still non-zero frequency values. So that's essentially what we've got here, this limiting value. That approaches -90 because these poles contribute 0, approximately 0, and this one pole at the origin looks just directly up. And so since, again, the poles come in the denominator, it gets that minus sign. And so for that reason, the Bode plot starts off at this -90 instead of at 0, because it has this pole located at the origin. We'll see a couple different variants of that as we go through some activities. So that's one consequence, and then the other consequence is this arc at infinity. And so just to kind of really digest what the Nyquist plot is showing us, we notice that the Bode plot, again, it starts at -90, so at very, very low frequency values, it's going to be -90. And so we can kind of see that. So -90 is this angle right here, -90. And so you can kind of see that this arc comes in, and if we were to zoom in at the origin, right here, this particular arc is coming in, and it's coming in like this. And so the tangent is indeed at this -90 angle. So this has this tangent of -90 going on here. And then as we increase the frequency, we're going to slide along the imaginary axis. And so we're going to start at -90, and then that's going to build up. This particular pole at the origin is going to continue to contribute that -90. These ones are going to contribute a larger and larger value. And so eventually they're going to get to the point where this is a very large point up here, close to infinity. These are going to look like they're contributing about 90 as well. So these are 90. The pole at the origin is 90, and so eventually we get to -270, 3 copies of -90. And so that's why we eventually get to 270. In between, we're going to pass through -180, and so that's that point here where we pass through -180. And then eventually this keeps going up, and this is a little bit deceiving. It looks like maybe this angle is not at 270, so minus 270 would be all the way around like this. And so you just kind of have to imagine that this is not to scale, and this really needs to be a lot further up before it really takes that arc out at infinity. So that's how this connects with the phase plot and the Bode plot. And then the other thing is to take a look at when the encirclements change directly using the Nyquist criteria. In this case, we have no unstable open loop poles. So for the system to be stable, we need 0 counterclockwise encirclements of the point -1. We can see that at this particular point, when k is equal to 1, so that's what we plotted for, this is just k is equal to 1 because this is just the real and imaginary parts of g of I omega. So at this point, the intersection point is at -1/2. And so that means that this point here is not encircled at all. But we can see that as we were to increase k, that this point would get shifted out. And in fact, since this is at -1/2, once we got to twice that, so k is equal to 2, this would shift it so that the point -1, so this is the point -1, this would be the case that you would be getting this crisscrossing happening right there. And then this would, again, loop back at the origin over here. So, and then what's interesting is take a look at the orientation. So here's our arrow. So if we've traced that back, that's pointing along this direction, which means that we're pointing along this way. And then that means that it's also pointing this way. And so if we were to increase that just a little bit more, so anything beyond k is equal to 2, so let's consider k is equal to 4. So then this would be intersecting at -2, and then -1 would be located inside. And so now that we have, this is in fact so we have to start here, start at the origin, and loop around. And so what we get here, we get half of an encirclement in the clockwise direction. And so then we have to continue following that around. So we continue following that along here and all the way around. And so then that reaches a point, once we get all the way around over to here, around that arc at infinity, now we've encircled this point one time. We've gone all the way around. And so we've encircled it one time in the clockwise direction, and then we continue and do that all over again to get one more encirclement. So in this case, we have 2 clockwise encirclements of the point -1. And so that shows us that any k value beyond k is equal to 2 leads to 2 counterclockwise and 2 clockwise, in encirclements of -1. So when we do this, the best idea to think about this is that you take a string and you fix one end of the string here, and it's kind of an elastic string, and then you trace it out. And what you want to make sure is that end of the string goes all the way around. And so in this case, notice that when we've only gotten to this point right here, we've only done half of an encirclement. And so then you have to go all the way around to here before you see that the string has gone all the way around from 0, an angle of 0, to an angle of -180, to now an angle back at 0 again.